Hello, thanks, Kim. Thanks for having us, and welcome to our session. And let me share the screen. Okay. In this session, we will take this chance to share the latest updates about how we can enable OpenJDK on RISC-V. And this is Sanhong, and I also invite my colleague Kevin to do the co-presentation for this topic. Kevin, maybe you can introduce yourself.
Hi, everyone. I'm Kevin, and from Alibaba, and I work on the Java compiler, and I lead the team to improve the performance on the Java. And recently, we started to work on the Java for RISC-V, and we think it's very interesting, and we are appreciated to contribute to the RISC-V community.
Okay,
thank
thanks.
you.
Okay, I think this is agenda. In my talk, I think I would introduce 4 parts. The first part, I will give you the overview about how Java has been used at Alibaba. And the second part is the major part. I will give you the update about how OpenJDK has been supported on RISC-V. I will talk about OpenJDK upstream status, and also talk about the Alibaba Dragonwell. It's our own in-house OpenJDK implementation maintained by Alibaba Java team. And then the last part, the third part is about talk about the benchmark evaluation and the optimization work we did. This is the part introduced by my colleague Kevin. The last part is talk about the future work, our plan for the next year, this year and the next year. Okay. Here is an overview about the Java usage at Alibaba. Actually, we are building our software based on broad ecosystem in Java. Almost all online applications are written in Java with about billions of Java code. And I just gave you, I just use 2 keywords to describe the characteristics of our Java application usage in Alibaba. The first thing is, I think, massive. Actually, we are using Java at a massive scale, and we have around million instances of JVM instance. And the second keyword is our architecture is distributed, and you know, we are build our Java application are service oriented, and each of our services are running in separate JVM, and they are talking each other by using RPC mechanisms. And for this slide, I just talking about the relationship between OpenJDK HDDK and Alibaba Dragonwell. And as I have mentioned, we have our in-house OpenJDK implementation. We call the HDDK internally. And you can look at this left picture. We in HDDK, we already developed a couple of features. For example, RISC-V, which allows Java developers to dynamically scale your memory utilization according to application needs. And we also build a WISP coroutine. You can use WISP coroutine to build user mode thread in Java, then allowing Java developers to write code in synchronous, but you can get the performance of asynchronous. For multi-tenant, we also you can run multiple Java applications in the same JVM instance safely. For JVM, actually it's a trace and replay compiler technology. You can using profile data to pre-compile Java code before the customer message is processed, so that you can optimize the warm-up cost introduced by Java application. We also did some GFR extension, and actually we co-work with OpenJDK community and backport the GFR to OpenJDK 8 just 2 years ago. And we also add more GFR events for more efficient diagnostics. And just 2 years ago, we open source HDDK as the Alibaba Dragonwell. You can look at this right picture. The features I mentioned, for example, multi-tenant, coroutine, warm-up, has been included in our open source version, Alibaba Jungle. In long term, I think we are planning to ship all of them to Alibaba Dragonwell to open source space, and we would like to collaborate with OpenJDK community for contribution. This is some introduction about Alibaba Dragonwell. Actually, the Chinese translation of Dragonwell is Longjing, which is a symbol of Chinese tea culture, which happens to be a characteristics of Hangzhou, where Alibaba headquarters is located. For Alibaba Jungle, we actually released 2 LTS long-term support version. One is Java 8, another is Java 11. We have a quarterly release cycle for both versions. And in Alibaba Cloud, Alibaba Dragonwell is our default JDK distribution. For this part, I just gave you update about the status, how OpenJDK is running on RISC-V. So far, you can say OpenJDK can run RISC-V successfully by using 0 backend support. Actually, it's a interpreter version, so it's very slow. And but you can run the real Java application on RISC-V successfully. And just in last year, Huawei contributed the initial porting work into their own JDK distribution, JDK 11, which brings the template interpreter C1 and C2 code gen support in OpenJDK space. And in this year, Alibaba just adopted Huawei patch in Dragonwell 11 internally. And I just remember 2 months ago, the initial port has been pushed into JDK sandbox development repository. This repository is maintained by OpenJDK community, and where the OpenJDK developers can collaborate and co-work on such a big change. If you are interested in, you can follow this link and go to GitHub and download the OpenJDK support for RISC-V code. For testing, actually the public test pipeline has been set up by using Eclipse Adobe Team. I think maybe if you are familiar with Java, I think you may be familiar with Adobe Team. Adobe Team is formerly known as Adobe OpenJDK, which used for producing vendor-neutral build of OpenJDK project. I just give a link here. We also put a test OpenJDK build on Alibaba Dragonwell website. If anybody interested in trying Java on this file, then you can follow this link and download this OpenJDK build and can then run Java on this file. As I have mentioned earlier, actually we already adopt Huawei patch in Alibaba Jungle 11. This is overview update about how we can enable Alibaba Dragonwell for RISC-V. For testing verification work, we already run some testing work. For functional related test, you can say we have 90% pass rate for G-track test. For JC stress test, we got 100% pass rate. For the failures in G-track test, I think we will continue the investigation and fix them in the coming months. And this is the first work for testing FVT. The second testing verification work is SVT, system verification test. Actually, we already run Spring Boot framework on RISC-V successfully. The last part is a major part. We did more performance evaluation work for Java on RISC-V by using OpenJDK. The three major benchmark we are using. The first is SpecGBB 205, and the second is SpecGBB 2050, and also including SpecGVM 208. We also run some JMH benchmarks. I think in the third part. Okay, I think I give you a notice. The Dragonwell 11 RV support will be released. Will be released. I think maybe 2 months later. I think in next part, I think I invite my colleague Kevin to introduce the benchmark work, how we can evaluate the performance work by using popular benchmark, and how we can find some opportunity chance and opportunities to do more optimization work for Java on RISC-V.
Okay, thank you. And hi, this is Kevin, and I start to introduce our work on the performance for JDK on RISC-V. And first, we want to try to evaluate the performance and compare the performance on RISC-V and with the performance on the ARM platform. So we choose the hardware. You can see the hardware configuration is the Raspberry board, and it has the 4 CPU core number, and the frequency is 1.5 gigahertz. But if we need a fair compare, so we limited the core number as the same as the RISC-V. So all the tests are running on the 2 CPU core number. Okay, so the benchmark we choose is SpecGBB 2005 and SpecGBB 2015. These benchmarks are usually used to evaluate the JVM performance. From the chart, it's the score of the test result, and the higher is better. We can see the RISC-V, the performance on RISC-V is about half of the performance on the ARM platform. And I think it's not a surprise, because the first they have some frequency difference. In RISC-V we have 1.2 gigahertz, and for the Raspberry we have the 1.5. And another factor is the JDK on RISC-V is not well tuned. So I think there's some performance gap between these architectures. And next, we can see another interesting test. It's one of the macro benchmark from the JMH test suites, and the test is used for evaluate the multi-thread performance. First, let's see the baseline test. It's the test running in the single thread mode, and we can see the score. So I think the score can be matches the difference of the CPU frequency. So from the single thread test result, I think the RISC-V could be compared with the ARC-64. But in the other tests, these tests are running in the multi-thread mode. So we will find the performance is not as well as the ARC-64. So ARC-64 maybe have double or triple the performance improvement. So it gave us some idea. There's some bottleneck in the multi-thread execution, maybe like atomic instruction or memory barrier or something else. So we will continue to investigate these issues and try to find the bottleneck. And yes, we have a lot of place where we can to improve the performance for RISC-V. And the next after the benchmark tests, we also do some improvements in the performance. So in this presentation, we just describe the two of them. They are specific for the RISC-V platform. The first is we try to support the compressed instruction on RISC-V, so it can give us about 4.4% in the spec JBB tests. And the second is we enhance the trap line stats in the jet code, and it can give us 6% improvements. So I will give you some detail about this optimization. So I try to describe the compressed instruction support in RISC-V. So we all know the RISC-V can support the compressed instruction. So in this with this instruction, we can use a small code size to improve the performance. So we use the Spring Boot application to evaluate the code size reduction, and we can see we can reduce about 20% in the Java, and some in the interpret code, and some in C1 and C2. C1, C2 are two different jet compiler in the hotspot, and we can see it can reduce 20% in the code size. So it's very good, and especially for the platform like RISC-V, and the code size footprint is more important, I think, for RISC-V. And after reduce the code size, we can find the performance also improved. So we think it maybe come from 2 points. The first is because code size is reduced, and the jet compiler can have more chance to inline the methods, and we have observed the more methods are inlined from the compiler log. And the second is the small code size can benefit for the eye catch. So we guess when we enable this optimization, the eye catch miss could be reduced, and so the performance can be improved. And here is an example of the jet code. So we can see it's the generated code for the Java method string.charadd. And without our optimization, the code size is 328. And after the optimization, it could be reduced to 280 bytes. And in this red area, we can find the code is replaced with the compressed version. So the size is reduced, and we can reduce size and gain the performance improvement. So another optimization is about the trap line. Why we need to do the optimization is about in RISC-V, the JAL instruction, it has a small jump range. It's about 1 megabytes. And compared to other platforms like ARC64, we will find the jump range has 128 megabytes. So it's a bigger difference. So in OpenJDK, it uses a trap line strategy for the method call. So when we try to call a method, we need to first to jump to the trap line and try to load the real address of the target method, and we do a second jump to the real address. So it's not efficient. So and the performance is impacted by this trap line. So we try to do some optimization for this case. So in next slides, I will show it's more clear about the optimization. So we can see the trap line strategy. For the JS junction, it will go into the stub, and in the stub, it will try to load the target address and do a real jump to the target. But if we find the method target is in the jump range, so we have the chance to update them. So during the runtime, we will find if the target is changed to match the jump range. So we will update this instruction in the save point. So at this point, all the Java threads are paused, so we are safe to update the jump address. So with this optimization, we can gain about 6% improvement in the benchmark. And in this slide, I just give some shorter description about our future work on the RISC-V. So the first is we plan to release the Alibaba Dragonwell for the RISC-V. So we are working on it. And another is we will continue to work with the OpenJDK community and try to give our port work and our enhancement to the community, and let the OpenJDK community to accept the port. So the RISC-V could be a supported platform in the OpenJDK. And another work is we will continue to evaluate the performance and try to find more optimization opportunity. So we will continue to work on the intrinsic support, and we also want to work with other RISC-V group and try to find is there some opportunity to work with the hardware expert. So, for example, in the JIT compiler, we usually we will often try to invalidate the I cache because the code is always updated. For the example, just like the GAL instruction. And in other platform, we say we provide some instruction in the user space. So it could be done easily. And for RISC-V, so far we need to go into the system core to invalidate the cache. So it looks a heavy operation. So we want to have a new instruction like the cache invalidate it. And we are also work with the RISC-V and Foundation, and we have the management runtime SIG is launched, and we are if anyone want to join us, and you can go to this link, and any comments are appreciated. And okay, thank you.
Okay, we are done. Thanks.